And for our last application of the ideal gas law, we're going to bring back stoichiometry and do a little gas stoichiometry. Gas stoichiometry is no different than all the other stoichiometry you've done earlier this year. You're going to have a starting substance A, and you're going to have some value of that substance that you're going to have to convert into moles of substance A. Then you'll go from moles of A into moles of B using the balanced chemical equation coefficients. And then once you have moles of substance B, you'll solve the problem to find what you want to know about substance B. The only difference is now we have a new way to find moles of our substance. We started with grams, we use molar mass. Then we started to talk about concentration of solutions, we use molarity. And now we're going to talk about gas values, and we'll use PV equals nRT to find our moles. So let's see this in action with this sample problem. Solid copper 2 oxide, when heated, will decompose into solid copper metal and oxygen gas. If 30 grams of copper 2 oxide decomposes at 65 degrees Celsius and 1.05 atm, what volume of oxygen gas should be produced in liters? As with any stoichiometry problem, the first step is writing the proper balanced chemical equation. What we're given at the start of the problem is the 30 grams of copper 2 oxide, and what we want is the liters of oxygen gas. So the solution is to go from grams of copper 2 oxide into mole of copper 2 oxide using the molar mass of copper 2 oxide. Then we'll use the coefficients from the balanced chemical equation as a mole ratio to convert from moles of copper 2 oxide into moles of oxygen gas produced in the reaction. And then here's where it gets a little bit different. We're going to stop our dimensional analysis here, solve for moles, and then plug that moles into our PV equals nRT equation. Then we can solve for volume by volume equals nRT over P, with our answer to 3 sig figs being 4.98 liters. Here are 3 gas stoichiometry problems that all relate to this chemical equation up here. Try them out and I'll be right back to show you the answers. So in this problem, we're actually going to use PV equals nRT first to find moles of our O2. We rearrange it to be PV over RT equals N, and then we input our values given in the problem to solve for the moles of O2 that would react. Then we do the stoichiometry part by taking moles of O2, converting it into moles of H2O, then the molar mass to get grams of H2O, which to 2 sig figs is 16 grams. In this next problem, we're actually going to do the stoichiometry first to find moles of O2, and then put that moles into the PV equals nRT equation to find the volume of that O2 gas, which to 3 sig figs will be 1,330 liters. And in this final problem, we're again going to do PV equals nRT first to find out how many moles of gas the CO2 would be if we had all these parameters of pressure, volume, and temperature. And then we'll do the stoichiometry, converting the 0.515 moles of CO2 into moles of our gasoline C8H18, and then using the molar mass of gasoline to find that we're going to produce 73.6 grams of gasoline C8H18. And just like before, we're going to have some limiting reactant problems where we're going to have to figure out which of the reactants will limit the production of our product. For example, in this reaction, we want to know the pressure of the hydrogen gas that will be produced when we react sodium metal with water. And we have 50 grams of sodium metal and 1.5 moles of water. Then we're going to write the balanced chemical equation for the reaction that's happening, and then find out how many moles of H2 gas each reactant is capable of making. I see that I have enough sodium metal to make 1.09 mole of H2, but I only have enough water to make 0.75 mole of H2. That means that my water is going to be my limiting reactant. It's going to limit the production of my H2 gas, and my sodium metal will be my excess reactant. My theoretical yield is the yield predicted by the limiting reactant, and I should not expect to make what the excess reactant says I'll make. And now lastly, I'll just take the moles of H2 gas I should make, rearrange my PV equals nRT equation to solve for pressure, and I'll find that my pressure to 2 sig figs is 8.0 atm. So again, try this next problem, and I'll be back to show you the solution in a moment. So once again, we write the balanced chemical equation, and then we're going to find out how many moles of ammonia, NH3, can both reactants theoretically produce. Since hydrogen can only make 0.92 mole of ammonia, that's going to limit the reaction, and so that'll be our limiting reactant. And 0.92 mole is how many moles of ammonia we should make in the reaction. Now that we have moles of our gas ammonia, we can then put it into PV equals nRT to solve the problem. And the pressure of the ammonia gas produced in this reaction should be 2.3 atm. But now I want you to think, is 2.3 atm the total pressure inside that 10-liter container? Well, before the reaction, we had both hydrogen and nitrogen gas in the chamber. The reaction happened, and all of the hydrogen gas was used to produce NH3, ammonia, and some of the nitrogen was also used to make the NH3, but not all of the nitrogen was used. Some of that nitrogen remains after, and that nitrogen that remains after is going to apply a pressure to the chamber as well. The 2.3 atm is only what the NH3, the ammonia, will be producing. The total pressure will be the sum of the ammonia pressure, which we know, plus the leftover nitrogen gas. Let's look at this further on the next page. Well, let's organize how many moles of everything we had at the start using this BCA table. We already know that hydrogen is our limiting reactant and will be used up entirely, and nitrogen is our excess reactant and only some of it will be used. We can find out how many mole of N2 will be used by doing a mole ratio of our limiting reactant, hydrogen, into our excess reactant, nitrogen. And then we see that we have 0.43 mole of N2 left over. So what pressure will this N2 provide to the chamber? Well, pressure is equal to nRT over V. Since the excess nitrogen is in the same chamber, it's going to have the same temperature and same volume values as we did for our product. And so the nitrogen gas that's left over is going to provide an additional 1.1 atm of pressure inside of our 10-liter container. And it turns out that when multiple gases are in the same container, the total pressure is just the sum of the individual pressures of each gas. This is known as Dalton's law, and we're going to look at this further in a later video. So for us, the total pressure in the 10-liter container will be the pressure of our ammonia gas we produced plus the excess nitrogen that remains. So the total pressure in our chamber is 3.4 atm.